Okay, hello everyone. Uh, Today we are going to talking about genetic algorithms from the artificial intelligence subject. So we already discussed previous week that optimization is the process of finding the best possible solution to the problem from the sets of available alternatives while satisfying the certain concentrates. So it means there are some possible alternatives, some possible solutions that among them the algorithm optimization helps us to find the best answer with considering some concentrates. You can see in the picture that from starting points, which is from the starting points, so the path going through the minimum. So optimizations helps us to going through this path to find the minimum point. Okay, some terms that we need for the optimization we have to be familiar that the objective function, which is the maximize or minimization, this is what we want to do, maximize or minimize. It can be cost, it can be time, it can be energy, it can be profit of the company. Decision variables, the inputs are the choices you can control. For example, for the cost, you can control the number of the staff, the materials you for the manufacturing process. Right? The concentrates is the rules and limitation. How many hours you can run the machine? Uh, how many months you can run for the for considering the maintenance of the machines? How many staff workings? How many laborers workings for each machines? So this is our concentrates. Okay, a factory wants to maximize this example. A factory wants to maximize profit by deciding how many units of the product A, uh, B, and B to produce, considering labor and material limitations. What is objective? What is desirable? And what is concentrates? For sure, objective function is maximizing the profit, right? These variables between will be the number of product A and B, and concentrates is the label and materials. We will be our limitation. Okay, different type of optimization. We have many types of optimization. The conventional one, the most conventional one is the gradient descent, is the iteratives, and um, and it works. It moves toward the directions going to the optimal points. Simplex methods that you are familiar is a part of linear programming problems. Move along the edge of the feasible region to reach the optimal vertex. We have meta heuristics optimization, which is the numerical way that works with the explore the searching space to find a near optimal solution within the limited reasonable time. So meta heuristics methods is a bunch of algorithms. It's type of the is a technique to which numerically search for the looking for the or search for the optimal points in the searching space. For example, in this case, in this example in the picture, you can see the dots. Red dots are the points that iteratively going to find the optimal points, which is in here. You can see also in here. Okay. So this table shows the different types of meta heuristics optimization, which and the inspiration and case using case. So algorithms such as GA, PSO, and colony optimization, simulated annealing, artificial bee colony, harmony searching, and firefly algorithms. For example, GA that we are going to consider in this lecture is the natural base based on the evolution, and the case study for the robot control. Feature selections. PSO is based on the swarms of the behavior for neural network tuning, trajectory planning. Okay, and colony optimization used for routing problems, right? And so on. You can see on this uh, table. Most of these kind of algorithms have a nature-based inspiration. Most of them they monitor the behavior of natural phenomenon, and they model it in mathematically to find mathematical algorithms. For instance, the genetic algorithms is based on the Darwin theory of evolution. J is a type of optimization algorithm inspired by the process of nature selection and genetics. Okay, you can see in the picture that gradually from apes we become the current human being. So it's based on the natural selections, process of natural selections that the evolution provided for us. So inspired of that, so we created the genetic algorithms. Genetic algorithms is based on the best adaptations and survival. It doesn't mean that the strongest can survive. It means the species that have the best adaptations they would survive. Okay, this is a history that on 1st July of 1858, Charles Darwin presented his theory of evolution, okay, before the Linnean Society of uh, London. Okay, John Holland made this inspired by Darwin theory. Um, Submitted a book, published a book named Adaptation in Natural and Artificial Systems in 1979, and introduced the basics of the genetic algorithms that we are going to uh, that we have nowadays and we are going to study. Okay, the definition of GA. GA algorithms are the class of the stat stochastic search algorithms based on biological evolution, based on the evolution theory. So two mechanisms like GA, we have evolution, encoding, and evaluation. Means we have the encoding of the genes, each populations, the genes, and evaluation of in each iteration or in each generation. It uses natural selection and genetics inspired technique known as crossover and mutation. So we have two techniques for the operations of the genetic algorithm. They call it crossover and mutation. Each chromosome consists of number of genes. Each chromosome, which is one, for example, population, each have the genes. Genes is respective are binary 0 and 1. That's why we need decoding to make a 0 and 1 meaningful for the algorithms. So the main components and process of the genetic algorithm, we have initialization of the chromosomes, initialization of each chromosomes. Each chromosome should be evaluated. Each individual, each chromosome of the in population should be evaluation. We have selection individual, or selection from the current population. Serves as a parents to the next generations. We have to select the genes to apply the crossover and mutation. Crossover are combines to create the offspring. Mutation give the chance to the algorithms to have to have the diversity in the algorithms, and also mutation helps to prevent algorithm from getting stuck in the local optima. Replacement and termination. Each uh, so in the replacement, the new generation and individual new generation from the offspring replaced with the previous one. So termination condition of the algorithms, whatever it can be, number of iterations, it can be some error, some, for example, percentage of the error. If our algorithms achieve, our algorithm will be stopped, will be terminated. Okay, steps of genetic algorithms. First steps is to represent the problem variables, domains, and chromosome. We have to set up our uh, algorithms. How many is the iteration? How many population? Size of the chromosome population, and probability for the uh, mutation and crossover. Except to define the fitness function, we have to find out what's our fitness function, what is our objective function for evaluation. So step 3 is initialization, random initialization of the first iteration. Step 3 is evaluation based on the fitness function of each initialized population. Then select the pairs. After this, after step 5 is how to make a next generation. Okay, so for the next generation, the selection of the parents to make the crossover, to apply the crossover, and apply the mutations. Then step 8 is going to back step 5. Repeat again to next gen evaluation, next generation evaluation, next generation evaluation until the termination condition satisfied. And here you can see the flow chart of the genetic algorithms. Start and initialization, evaluation, calculate the fitness function, uh, checking the termination condition. If yes, finish. If no, the select pair of chromosomes, making the offspring from the crossover, apply mutation, um, replace the offspring and muted uh, genetics with the previous ones, creating a new generation. This loop create the new generations, and again evaluations, again checking satisfactory of termination. If yes, algorithm finish. Maybe these iterations, this loop continue for 1000 times, 2000 times, 3000 times. Depends on the feature of our algorithms, of the parameters that we define, how many iterations we want our algorithms to run. Genetic algorithm operations, as we discussed, as mentioned, two crossover. We have two operations for genetic algorithm. They call it crossover and mutation. Okay, how does it work? Okay, look at this uh, cycle here. We have this generation, the chromosomes X1, X2, X3 until X4. Each chromosome have genes that 1 0 1 1 0 0 0 1 0 0 0 0 0 1. If we decode this chromosome, we've reached the number 36. Okay? These generations apply to the roulette wheel for the selection. This part is selection, roulette wheel. After selection of the parents, crossover starts. As you can see, X6 and X2 are selected to be a parent. X6 and X2. Two digits, two genes of the X6 and two genes of X2 are selected to crossover, to swap. So 0, 0 comes to here, as you can see. 0, 1 goes to x2, as you can see, 0, 1. So x6 here is different from the x6 in the mutation part. Okay, that's a crossover. Same for x1 and x5. x5, same for x2 and x5. In the mutation, for example, x1 and x2 selected by the roulette wheel, okay, to swap one of the digits, one of the gens. 0 turn to 1, if 1 turn to 0, if 0 turns to 1. Okay, and the next generation created. After this evaluation, again, selection, crossover, mutation, new generation, evaluation, selection. Okay, that's the cycle for crossover and mutation. And how does it work? Okay, for instance, in this example, crossover works like this, that if we have 4 points of the crossover, so 4 points means point equal to 4. We have two parents of x and y. X and y are the parents. So we have 9 genes in this chromosome. 1, 0, 0, 1, 0, 1, 0, 1, 1. In Y also we have 1, 1, 1, 0, 1, 0, 0, 1, 0. So we count from the left, 1, 0, 0, 1, 4. 1, 2, 3, 4. Okay, we put point in here. We put point in here. And 1 point in here. Okay. So this one will be swap go in here, and these 5s will go to here. So as you can see, compare, you can see that these 5 gens replace here. The production of the crossover, we call it offspring. Offspring produced by crossover cannot contain information that is not in the population. Okay, then if we apply only crossover, what will happen? Each information of each generation will be passed to the next generation, will be passed to the next generation, will be passed to the next generation. We cannot have a significant change in each generation. To cover that, genetic algorithms offer us the mutation. Before going to mutation, let's see this example for crossover. That we have parents, which is blue, for example, yellow and pink. The cross or the offspring would be blue plus pink, and can be yellow plus green, right? And same in here, the pink is replaced by the black, green. See? Okay. So as we were discussing about the mutation gives chance to algorithms to have the diversity in the algorithms. Okay. So mutation, operation of the GA, of course, inspired from the nature, which is rare in the nature, represent a change in the genes. It may lead to the significant improvement in the fitness, but more often has the harmful results. Like a Down syndrome is a mutation, but we don't know that it's good. It won't be a good or harmful change if the mutation happen, right? So its rule is to provide a guarantee that the search algorithm is not trapped on the local optima. This is the benefits of the mutation, because is it makes our searching a space wider. Maybe mutation is only crossover is only limited on the some certains of the value, only playing with some certains of the value informations of chromosomes, but mutation give chance to see uh, other area than the searching space. As we discussed before, this is how the mutation works. After the crossover, mutation apply. Mutation apply in the X1 that should swap, for example, second gen from 0 to 1. Okay? From 1 to 0. For X2 from 0 to 1. For instance, in here, mutation happen in the digit number 2, 0 change to 1, digit number 4, 1 change to 0, then digit number 1 or gen number 1 that change from 1 to 0. This is how the mutation works. Okay, what is roulette wheel selection? Roulette wheel is the most commonly used chromosome selection technique is the roulette wheel. So you can see then the roulette wheel is like a pie chart. Okay, so it's like this surface, this rule will rotate, and these pointers very stop. It's like a games that you play, right? Very stop. The regarding chromosome will be selected. For example, is pointing on the gray area. Gray area is X6. So in this case, X6 is selected. If a stop in here will be, I think, X1 is selected. So how this roulette wheel created based on the bar chart of the percentage based on the value of each chromosome. Okay, the area that the slice within the wheel is equal to the chromosome fitness ratio. This percentage of the chromosome fitness ratio. Okay, for instance, the chromosome X5 and chromosome X6, X5 and X6 occupy the largest area because 25 and 24%. Chromosome X3 and X4 occupy the less. This one, these two. The roulette wheel is a spawn, means rotate, and when the array, this pointer, the array comes to the rest, on, means a stop on one of the segments, the corresponding chromosome is selected. The corresponding chromosome will be selected. For example, here is X6. Now we talk about the decoding. As I mentioned in here, each chromosome, X1 for example, have one. If we decode, we count the value 36, 44, 14, 14, 56, 54. How we get this value from each chromosome? So that the point is, we have to change from base 2, which is binary 0, 0, 1, 0, 1, 0, to 10, base 10. Base 10 is the normal value that counted until 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is based on 10. It's a normal that you always face in your life. Everything is based on 10. So how to do that? Look at this example. It's based on 2, which is this value, this number 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0. Okay, so look at how many. I make it with a pen. Okay, so look at here. The value of the chromosome times 2, the power of 0. The value of the chromosome, which is 1, times 2 the power of chromosome, the power of 1. The value of chromosome, which is 0, so we are moving backward, which is 1, number 0 here, 1 times 2 power of 1. So from back, each now value have the index of 0, 1, 2, 3, 4, 5, 6, 7. Last one is 7. Okay, so we start backward from 0 is easier way. If we go forward, maybe you don't know which number to you start. Backward is easier. So 0 times 2 power of 0. Index 1, index 2, index 3, index 4, 3, 4, 5, 6, 7. Okay. After that you apply the calculation and you will reach a value 138. This is the value in the base 10. This is the decoding. And see another example. Started from 0, 1, right? 1 times 2 power 0. 1 times 2 power 1. 0 times 2 power 2. Okay. 1 times 2 power 3. And same pattern. Continue until the end. After this slide shows the trapping on the global and optima and the local optima. If you can see here, we have the top, the mountain, and here we have another mountain. This mountain for these two are the maximum, but it is the maximum of all the surface. As we can see here is the highest. And gradually the values are going to the local. This means is trapping to the local optima. They are not trapping, they are not looking at here. They are looking on the local optima. Compared to this, that the algorithms already could find the highest point, the maximum points. Right? So this one is global optima, which is correct. This one trapping in the local optima, which is, we can say the algorithms is deceived. That the how to say that the dark points that the algorithms can go, trapping in the local optima. Okay, what is the performance graph? Okay, what is the performance graph? You can see this is, for example, the performance graph. This example is maximization. So the y-axis, the x-axis here is the generation, and y is the fitness. For example, in generation 2, the fitness is 0.4, is 4 is 0.8, is 8 is 0.15 something. Okay, you can see as the algorithms are going forward, means the number of iterations increase, the value of the fitness is lying on the certain value, is going to be sustainable. They call it convergence. So this performance of this graph shows that after iteration 12, for example, to iteration 20, the algorithms is lying to the 1 point, for example, 7 8, for example here, 1.7, for example, 1, right? So it means the maximum value of this algorithm is 1.7, and the algorithms is converging. This shows that our algorithms is going functioning properly, looking at the and converging and narrowing down the searching space, and gradually in each iterations is converging, reaching to the area, like this picture, reaching to the area from this become this, right? So converging to the maximum point. Okay, let's see one example. So this function is given to us. We call it, for example, fitness function. Okay. In this table we have x1, x2, x3, x4, x5 and x6. This is the chromosome labels. And this is chromosome is string. Chromosome strings means before being decoded. Chromosome strings in the binary. After being decoded, as we discussed before, with the value, with the decoding from the base 2 to base 10, we have 12. For example, 14, 1, for, 12, 4, 1, 14, 7 and 9. After decoding, this will be decoding of the chromosome. After that, what we have to do, we have to substitute this decoded chromosomes inside our fitness function. For example, in this case is 15 times 12 power of 2 minus, sorry, no power of 2, 12 power of 2. Okay, if we apply that, we will reach to this value, which is the chromosome fitness. Okay, then we have to calculate the fitness ratio, right? How to do fitness ratio? The last column is show the individual columns chromosome fitness, population, total fitness. Okay, the ratio determine the chromosome chance of being selected for the mating. Mating means parenting for the crossover and mutation. Does the chromosome X5 and 6 stand a fair chance while the chromosome, okay. What's the formula is for defining the ratio is this one. This one shows each chromosome fitness over the total chromosome fitness. Means 36, for example, over 36 plus 44. My mouse pad is not good, I cannot write it properly, but I can explain that plus 44 plus 14 until the end. If you apply this, you will reach to 36. For the next one, you make 44, you have to do 44 over again 36 plus all of them, 36 plus 44 plus from top to bottom plus until 54. Again for this 14 over the total. So after you calculate times 100, you will reach this value. This is the fitness ratio, and you can make a pie chart based on your fitness ratio. You can make the pie chart. This pie chart represents your roller field for the selection. So as you can see, this for x6 and for this one x5, 6 and 5 have the highest chance to be selected for mating. For example, if this one rotate, maybe once stuck in here, stop in here, so which is for example x1. You can see this is 0, 16, 36, 49 until 100. Another time we run is reach stuck on x, for example 3. So this one, these two will be selected for crossover. Okay, for the mating, as we discussed, they swap the digits. Okay, what else? Okay, summary. The GA is a type of iterative algorithms which is inspired by Darwin evaluation theory. The GA is used to optimize the parameters of an objective function. The main part of the GA are initialization, evaluation, crossover, mutation, and termination. Okay, I think that's all for this lecture. And good luck, and thank you for watching.